Good day to IR Alpha Type and IR Mid Audit panel for this presentation. I'm Chua ID AA20216, and my supervisor is TS Dr. Martin. I'm doing research on the field of structure, and my title of research is Simulation of Cylinder Weather Type in RC subjected to glass. For my presentation, there will be 7 parts as shown. I will start from research background. Rising costs of reinforced concrete in construction have led to the development of the wide RC slab that can reduce expenses by replacing the assets concrete with void formers. Although not in war zone, residential areas face potential blast load from liquefied petroleum gas LPG exposure. Understanding the behavior of RC slabs under blast condition is crucial for safety. This knowledge is vital for enhancing the safety of this structural element. Next, will be proven statement. The RC structure constructed for residential is not designed to withstand the blast load. However, the LPG using in the kitchen is possible to explode. Recent innovation on the slab, weather slab is introduced. Therefore, the purpose of this thesis is to study the cylinder weather RC slab in reducing the percentage of concrete and the strength of the slab when it is subjected to blast load. There are 2 main objectives in this research, which are to investigate the cylinder weather RC slab subjected to blast loading numerically by using commercial FES software and SysAutoDyne. The second objective is to determine the effectiveness of cylinder weather in RC slab as blast-resistant structure based on percentage of reduced concrete and arrangement of cylinder wall. Next, I will proceed to literature review. All these authors conduct research that is related to blast. Now, I will move on to research methodology. There will be 2 parts for my research methodology. For the first part, round 2013 is taken as reference to conduct the numerical simulation in SysAutoDyne for solid RC slab subjected to blast load with an accuracy of mesh sensitivity. The process needs to be repeated until achieving similar result to round 2013. Then it can be proceeded to second part. The second part will share the same process but changing the slab to cylinder with RC slab. So this is the drawing related to my study. RCS1 is a solid slab, where RCS2, 3, and 4 is a cylinder void RC slab with different arrangement. So the percentage of concrete reduced is shown in table 1. The cross-section of the slab is also shown at the lower left of the slide. In this study, numerical analysis will be conducted by SysAutoDyne. The arbitrary Lagrange Euler ALE solver is employed in this case. RC slab is modeled by a Lagrange subgrid, where A is expressed by Euler. In order to conduct blast analysis using AutoDyne solver, the solid elements of the RC slab are first identified within the ANSYS workbench. The behavior of the concrete is described using the CONC 33 MPa material model in AutoDyne's material library, where steel reinforcement is described using the steel 4340. AutoDyne uses an axial symmetric wedge shape model for simulation. It is occupied by a calculated charge circle designed for 2 kg of TNT material. A field file is generated containing the blast overpressure history, which will be utilized for subsequent remapping function in various 3D air volume types. In AutoDyne material library, the standard constant for air is employed to characterize its behavior, utilizing the ideal gas EOS. On the other hand, the behavior of TNT is described using the Jones-Beckley EOS method. Now, I will proceed to mesh sensitivity. Few size of mesh has been tried in this study to determine the most appropriate mesh size for this study. Firstly, I start with Coulson mesh, which is a 50mm mesh, followed by 25 and 15. 50mm is not the most suitable mesh, but I'm not able to proceed with final mesh due to equipment limitation. Low mesh size require longer time to simulate the model and high performance equipment. Next, it will be the gauge location. Gauge will be used to obtain outcomes from the event. Gauge 1, 2, 3 will be used to obtain a value of air pressure. Gauge 10, 11, 12 is for displacement, and gauge 19, 22, and 25 to get the effective strain from bottom reinforcement, where gauge 28, 31, and 34 for top reinforcement. So I will proceed to result and discussion. From the result obtained, it can be seen that the damage pattern of my slab in 10 milliseconds is almost similar to Wang 2013. They will be different due to Wang used a 3mm mesh to run the simulation, but I only used 50mm. At 1.75 millisecond, it can be seen that the blast starts from the middle of the slab because it is located at 500mm upright center of the slab. From the comparison, the slab created has been validated to be identical to one made by Wang 2013. This slide shows the damage pattern of RCS1. Before I explain further, Figure 22 shows the vector of TNT after it has been remapped into the RC slab model. For all slides, I will only explain detail on result of 8 milliseconds because the most accurate result is about 9 milliseconds. 0.5 millisecond and 5 millisecond is to show the propagation of the blast mode. In figure 21 and 22, cracks are detected at the center area expand to both left and right side of the slab, caused by the intense pressure generated by the explosion and the friction force. Damage at the top of the slab is lower compared to bottom due to initial explosive generated compressive wave first reached the slab's top surface, then propagated to the bottom and transition into tensile wave. Due to lower tensile strength compared to compressive strength, the bottom surface of the concrete slab experienced more severe cracking and damage than the top surface. So this is the strain time history of the RCS1. The maximum effective strain at bottom reinforcement is 30.21 times 10 to the power of -4. For top reinforcement, the ultimate effective strain is 18.07 times 10 to the power of -4. From the comparison between two graphs, the strength of the bottom reinforcement is higher than the top reinforcement. This is because the bottom side encountered higher deflection than the top side. Now, I will proceed to the damage pattern of RCS2. It reveals that the crack initially appear in the middle of the slab. Numerous compressive cracks and tensile cracks extend readily across the top and bottom surface of the slab, with the compressive cracks generally shorter in length compared to the tensile cracks. Besides, spalling was observed on the side of the slab. The concrete's poor tension resistance led to a crater of tensile spalling on the rear surface of the slab. So this is the strain time history of RCS2. The bottom reinforcement experienced a maximum effective strain of 27.9 times 10 to the power of -4, while the optimal effective strain for top reinforcement is 18.65 times 10 to the power of -4. From the graph, we can observe that the effective strain value moves to the peak and back to the original position. It can be explained as the material of reinforcement is flexible. Hence, it can be concluded that the steel reinforcement is able to withstand tensile force due to its flexibility. So this is the result for RCS3. The figure illustrates a crack originating at a slab center, extending radially across its top and bottom surface, where bottom encounter larger area of crack. There is a higher occurrence of radial and circular cracks on the top surface of this slab compared to RCS2. However, the crack area occurred in RCS3 is a bit smaller than RCS2 since this RC slab has lower volume of work. Similarly, spalling was observed on the side of the slab. The bottom reinforcement reached a peak of effective strain of 31.19 times 10 to the power of -4, while the top reinforcement achieved an optimal effective strain of 14.55 times 10 to the power of -4. So this is a damage pattern of RCS4. It is observed that the crack pattern starts at the center, same as RCS2 and 3. It expands radially to the whole slab. From the bottom view of the slab, it exhibits the largest area of crack compared to RCS1, 2, and 3. Swelling also happened in this slab. So the bottom reinforcement attains a maximum effective strain of 32.63 times 10 to the power of -4, whereas the top reinforcement reached an optimal effective strain of 20.54 times 10 to the power of -4. This is the comparison of damage pattern for 4 RC slab at 8 milliseconds. From the graph, it reveals that the pressure reached a maximum of 2.96 times 10 to the power of 4 kilopascal at gauge 1. This gauge received the highest pressure because it is the nearest gauge to the destination point. Pressure received by all slabs will be the same since the same weight of TNT is used. The high pressure wave generated by TNT can create a surface tensile stress on the sides of the slab facing the blast, resulting in swelling and permanent deformation. From the graph of displacement at gauge 10, it can be concluded that the displacement of RCS1 will be the lowest, followed by RCS4, 3, and 2. From my point of view, this happened because the solid slab has the higher volume of concrete compared to the slab with wall. Lower concrete volume indicate that the compressive strain will be lower down. Besides, the value of displacement in gauge 10 will be greater than gauge 11 because of gauge 10 is nearer to the junction point, and the value obtained at gauge 11 may not be so accurate. For gauge 12, the value of displacement is not consistent because it is located at the fixed support. Now I will proceed to conclusion and recommendation. For the result, it can be concluded that the displacement observed for RCS3 does not exhibit significant variation when compared to RCS4. At 8 milliseconds, the displacement for RCS3 is a negative 65.1 meter, while it is a negative 57.97 meter for RCS1, resulting in a percentage difference of 10.95%. The difference is still in acceptable range. Similarly, RCS4 exhibit a displacement of negative 60.79 mm, leading to a percentage difference of 6.62% when compared to RCS3. However, RCS3 reduces more concrete than RCS4. Thus, it can be concluded that RCS3 demonstrates a greater effectiveness. Strength of a solid slab is greater than cylinder void slab due to reduced compressive strength of cylinder void. The higher the volume of cylinder void, the higher the displacement of slab when exposed to the same load. So I have some recommendation after I have done this research. So the first one is weight of the slab can be reduced by using another alternative, such as change the liquid used to mix with cement to micro nano bubble. And second is replace some portion of traditional aggregates such as gravel or stone with lightweight aggregates like expanded clay, shell, or pumice to reduce weight. Third one is apply post-tensioning method in RC slab to counteract applied load so that the displacement can be reduced. So this is the reference that I have been used in completing the research. Thank you.